Picture this, a tiny speck in the vast darkness of space, blinking on and off with such perfect rhythm, it could rival the most precise clock ever built. These are pulsars, cosmic lighthouses that flash with breathtaking regularity, some keeping time better than atomic clocks here on Earth. But how? What makes these distant stars pulse with such machine-like precision? Pulsars are the collapsed cores of massive stars that went out with a bang. Supernova explosions so powerful they crushed matter into an ultra-dense neutron star. Spinning at dizzying speeds, these stellar remnants fire beams of radiation from their poles like interstellar searchlights. From our vantage point, each rotation sweeps that beam across Earth, creating the illusion of a flashing cosmic beacon. The real magic lies in their consistency. Some pulsars rotate hundreds of times per second without missing a beat, their flashes arriving with a predictability that defies the chaos of the universe. They're nature's perfect timekeepers, and their secrets could rewrite how we understand space, time, and even gravity itself. Stick around, we're about to unravel why these celestial metronomes tick with such unshakable precision, and how they might one day guide spaceships across the galaxy. Now let's rewind the cosmic clock to where it all begins, the explosive birth of a pulsar. Imagine a star, not just any star, but one several times more massive than our Sun. When such a star runs out of fuel, its core can no longer fight the crushing force of gravity. In a matter of seconds, the star collapses inward, triggering a cataclysmic supernova explosion that outshines entire galaxies. What's left behind is a neutron star, the dense, city-sized remnant of that stellar giant. This is where the magic happens. As the star collapses, its core gets squeezed into a sphere no bigger than a city, yet packing more mass than our Sun. The laws of physics go wild here. Protons and electrons merge into neutrons, creating matter so dense that a single teaspoon would weigh 1 billion tons on Earth. But the real showstopper is the spin. Just like a figure skater pulling in their arms to spin faster, the collapsing star speeds up dramatically, rotating hundreds of times per second. And then there's the magnetic field, trillions of times stronger than Earth's. These unimaginable forces channel particles into narrow beams shooting out from the star's poles. When these beams sweep past Earth, we see the pulsar's iconic flash. It's a cosmic lighthouse born from destruction, yet ticking with near-perfect precision. Next, we'll dive into the moment these flashing giants were first discovered and how they stunned astronomers with their otherworldly rhythm. Now, let's step into one of the most thrilling chapters in astronomy, the moment pulsars were first spotted. Picture this, it's 1967, and a young graduate student named Jocelyn Bell Burnell is meticulously scanning the skies with a radio telescope she helped build. One day, she notices something bizarre, a series of rapid, rhythmic pulses beaming from deep space, ticking with such precision they almost seem artificial. At first, she and her team jokingly labeled them LGM signals, short for Little Green Men. Because the pulses were so regular, they wondered if they'd stumbled upon an alien broadcast. But the truth was even more extraordinary. These weren't messages from extraterrestrials. They were the first recorded signals from a pulsar, a spinning neutron star flashing like a cosmic metronome. Jocelyn's discovery shattered our understanding of the universe. Before this, neutron stars were just theoretical. No one had proof they existed. Now, here was undeniable evidence, and it came with a twist. These objects weren't just dense remnants of dead stars. They were natural precision clocks ticking with staggering accuracy. This breakthrough didn't just add a new object to the cosmic catalog, it rewrote the rules of astrophysics. Pulsars became tools to test Einstein's theories, map the galaxy, and even hunt for gravitational waves. And it all started with Jocelyn's sharp eye and a signal so strange, it briefly made scientists wonder if the universe was winking at us. Next, we'll unravel the Lighthouse model, the brilliant explanation for why these cosmic beacons flash in the first place. Now, let's shine a light on the secret behind those rhythmic cosmic flashes, the Lighthouse model. Imagine a spinning neutron star, its surface crackling with energy. But here's the twist. Its immense magnetic field, trillions of times stronger than Earth's, funnels radiation into two narrow beams shooting out from its magnetic poles. These beams aren't fixed, they sweep through space like the rotating beam of a lighthouse. And just like a distant sailor only sees the lighthouse flash when it's pointed at them, we on Earth only catch those brilliant pulses when one of those beams swings in our direction. This cosmic choreography explains why pulsars appear to blink with such perfect regularity. Each rotation, the beams carve out a path in space, and if Earth happens to lie along that path, we get front row seats to the show. The faster the pulsar spins, the quicker the flashes. Some flicker hundreds of times a second, while others take leisurely seconds between pulses. But no matter the speed, the precision is mind-bending. It's nature's ultimate strobe light, powered by gravity and magnetism, ticking away with a reliability that rivals our best atomic clocks. What's even wilder, the beams themselves aren't just light, they're packed with radio waves, X-rays, or even gamma rays, depending on the pulsar. And because these stars are so perfectly balanced, their spins barely waver, making each flash arrive right on schedule. Next, we'll dive into how some pulsars spin faster than a kitchen blender, and what that tells us about the extreme physics at their cores. But here's where things get even more fascinating. Pulsars don't just flash, they do it with jaw-dropping precision. Picture a neutron star spinning hundreds of times every single second, its beams slicing through space like a cosmic metronome. These aren't just fast rotations, they're staggeringly stable. Over decades, some pulsars keep time so accurately that they rival the atomic clocks we use here on Earth. In fact, the most stable pulsars lose or gain just a fraction of a second over millions of years. That's why scientists often call them the universe's natural timekeepers. Think of it this way: if you had a pulsar ticking away in your backyard, you could set your watch by it, and it would stay perfectly synced for generations. This incredible stability comes from their sheer density. A pulsar packs the mass of our sun into a ball the size of a city, making it so compact that even the tiniest wobble is smoothed out by gravity's iron grip. Unlike Earth, where earthquakes or ocean tides can subtly alter our planet's rotation, pulsars are nearly immune to outside disturbances. Their spins are so consistent that astronomers use them to test Einstein's theory of relativity, measuring how gravity bends spacetime around them. And here's the kicker: some pulsars are even more precise than the atomic clocks we rely on for GPS. While our best human-made clocks might drift by a billionth of a second per day, certain pulsars stay locked in rhythm with almost no variation. That's why projects like NASA's A Nicer Experiment are exploring how future spacecraft could navigate deep space using pulsar flashes as cosmic GPS signals. Up next, we'll zoom in on the speed demons of the pulsar world, the millisecond pulsars that spin faster than a jet engine's turbine, and what their whirlwind lives reveal about the universe's most extreme environments. Now let's turn our attention to the speedsters of the pulsar world, millisecond pulsars. These cosmic sprinters spin hundreds of times every second, making even regular pulsars look sluggish by comparison. But how do they reach such dizzying speeds? The secret lies in their cosmic dance with a companion star. Over millions of years, these pulsars siphon off gas and matter from their stellar partners, a process called accretion. As that stolen matter crashes onto the pulsar's surface, it transfers energy, spinning the pulsar faster and faster, like a figure skater pulling in their arms to accelerate a twirl. What makes millisecond pulsars truly special isn't just their speed, though. It's their role as cosmic laboratories for testing the limits of physics. Because they're so stable and fast, they're perfect for putting Einstein's theory of relativity through its paces. Scientists track their pulses with extreme precision, watching for tiny delays caused by the warping of spacetime around them. These subtle shifts confirm predictions about how massive objects bend the fabric of the universe, proof that Einstein's century-old equations still hold up in the most extreme conditions. But the surprises don't stop there. Millisecond pulsars are also key players in the hunt for gravitational waves, ripples in spacetime caused by cataclysmic events like colliding black holes. By monitoring networks of these pulsars, astronomers can detect minute changes in their rhythms as passing gravitational waves stretch and compress the space between them. It's like turning the entire galaxy into a giant detector with millisecond pulsars as its ultra-sensitive heartbeat. And here's the wild part. Some of these pulsars are so efficient at stealing matter from their companions that they eventually consume them entirely, leaving behind a lone, hyper-fast spinner. Others, locked in tight orbits, continue their cosmic tango, offering clues about how binary systems evolve. Whether as solo acts or dynamic duos, millisecond pulsars remind us that the universe is full of natural wonders that push the boundaries of what we thought possible. Up next, we'll explore the invisible forces behind these flashing beacons, the unimaginably strong magnetic fields that shape their brilliant beams. Now, let's pull back the curtain on the invisible powerhouse behind every pulsar's flash, its magnetic field. Imagine a force so strong it could rip the atoms right out of your body from thousands of light years away. Pulsars wield magnetic fields trillions of times more intense than Earth's, and these fields are the architects of their iconic beams. Here's how it works. Charged particles like electrons and protons get caught in the pulsar's magnetic grip near its poles. As they spiral along these field lines at nearly the speed of light, they release bursts of radiation, creating the focused beams we detect as flashes. But these magnetic fields aren't just static forces. Over time, they slowly lose energy like a battery running down. This decay has a direct effect on the pulsar itself. As the magnetic field weakens, it can't accelerate particles as efficiently, and the beams lose some of their punch. More importantly, this energy loss also taps the brakes on the pulsar's spin. Think of it like a spinning top. The slower it turns, the more it wobbles. For pulsars, that means their flashes become less frequent as they age, stretching from milliseconds to seconds between pulses over millions of years. What's fascinating is how this magnetic slowdown reveals the pulsar's life story. Younger pulsars with their stronger fields spin wildly and flash rapidly. Older ones, their fields diminished, grow sluggish and quiet. It's a cosmic clock winding down, ticking ever slower until one day the beams fade entirely. Yet, even in their twilight, these magnetic giants leave behind clues, helping us piece together how neutron stars evolve, and ultimately, how the universe itself shapes the fate of its most extreme objects. Next up, we'll see how astronomers use entire networks of pulsars as a galactic-scale detector, listening for the faintest whispers of gravitational waves. Now, picture this: an entire galaxy turned into a precision instrument. That's exactly what pulsar timing arrays do. By linking multiple pulsars across the Milky Way, astronomers create a network so vast it acts like a gravitational wave detector the size of our galaxy. Here's the genius part. As gravitational waves, those faint ripples in spacetime predicted by Einstein, pass through the cosmos, they subtly stretch and squeeze the fabric of space itself. This tiny distortion affects the timing of pulsar flashes ever so slightly, delaying some while speeding up others by mere billionths of a second. Think of it like a pond's surface disturbed by a passing boat. The ripples change the water's shape, just as gravitational waves alter spacetime. Pulsar timing arrays measure these minuscule delays across dozens of pulsars, piecing together a map of gravitational waves from colliding supermassive black holes or even echoes of the Big Bang. The longer we observe, the clearer the signal becomes, like tuning a radio to catch a distant station. What's truly groundbreaking is how these arrays don't just detect waves, they reveal their sources. By comparing timing deviations across different pulsars, scientists can trace the waves back to cosmic collisions billions of light-years away. It's like turning the Milky Way into a giant ear, listening for the universe's deepest whispers. And with projects like NanoGrav and the Square Kilometre Array expanding these efforts, we're on the verge of unlocking secrets about black holes, dark matter, and the very structure of spacetime. Up next, we'll shift from the cosmic to the artistic, how pulsars' rhythmic flashes have inspired everything from hit songs to sci-fi lore. But let's take a moment to listen, because pulsars don't just flash, they sing. When scientists convert their radio signals into sound, these cosmic metronomes reveal an eerie, hypnotic rhythm. The most famous of these is CP1919, the pulsar whose steady beats were immortalized on Joy Division's album Unknown Pleasures. Its repeating pulses, slowed down to audible frequencies, sound like a heartbeat from the depths of space, mechanical yet hauntingly alive. Artists aren't the only ones mesmerized. For astronomers, these sounds are more than music, they're data. Each click and hum carries clues about the pulsar's spin, magnetic field, and even the interstellar medium it travels through. Faster pulsars produce rapid-fire ticks, while slower ones echo like a distant drum. Some even glitch, their rhythms stuttering suddenly, offering glimpses into the turbulent physics inside neutron stars. What's fascinating is how these cosmic rhythms bridge science and art. Composers weave pulsar beats into electronic music, turning stellar vibrations into melodies. Filmmakers use them to score alien landscapes, their otherworldly tones perfect for evoking the vastness of space. And for listeners, these sounds make the universe feel tangible, a reminder that even in the silence of the void, there's a pulse, a rhythm, a cosmic dance we're only beginning to hear. Next, we'll uncover how pulsars, once thought to be sterile dead stars, surprised us by harboring planets of their own. Now, here's something that defies all expectations. Pulsars, those relentless cosmic clocks, aren't just ticking alone in the dark. They've got company. In the early 1990s, astronomers made a jaw-dropping discovery. The very first planets ever found outside our solar system weren't circling a sun-like star, they were orbiting a pulsar. Not just any pulsar, but Pulsar B 1257+12, a spinning neutron star that should have been the last place you'd expect to find worlds. These aren't your typical planets, nicknamed zombie worlds. They're the ultimate survivors. Imagine this: their parent star once exploded in a supernova, a blast so violent it should have vaporized anything nearby. Yet somehow these planets endured. One theory suggests they might be the scorched remains of gas giants, their outer layers blasted away, leaving behind dense, rocky cores. Others think they could be second-generation worlds born from the debris of the supernova itself, like phoenixes rising from stellar ashes. What's even wilder, the conditions there, bathed in intense radiation and gravitational chaos, these planets are anything but hospitable. Their skies, if they have any, would be lit by the pulsar's deadly beams, sweeping across them like a cosmic strobe. Yet their very existence challenges what we thought we knew about planet formation. If worlds can form or survive in the aftermath of a star's self-destruction, where else might planets be hiding? This discovery didn't just expand the cosmic real estate, it rewrote the rules. And it all started with a pulsar's steady beat, a rhythm so precise it revealed whispers of worlds where no one thought to look. But here's where pulsars go from being cosmic curiosities to something straight out of science fiction. They could become the ultimate GPS for the galaxy. Picture this: you're an astronaut light years from Earth with no familiar stars to guide you. How do you find your way? Enter NASA NICER mission, short for Neutron Star Interior Composition Explorer. While its main job is studying neutron stars, it's also testing a revolutionary idea using pulsars as interstellar navigation beacons. Think of it like this: pulsars flash with such mind-boggling precision that their rhythms are more reliable than the best atomic clocks we've built. By tracking the timing of these flashes from multiple pulsars, a spacecraft could triangulate its position in space, just like GPS satellites help your phone pinpoint your location on Earth. The difference: pulsars don't need batteries or maintenance. They've been ticking for millions of years, and they'll keep going long after we're gone. NASA already run successful tests with the Sextant experiment, short for Station Explorer, for X-ray timing and navigation technology. Using X-ray detectors on the International Space Station, they've pinpointed the station's position in orbit with pulsar-based navigation accurate to within just a few miles. Now imagine scaling that up for a ship headed to Mars or beyond. No more relying on shaky radio signals from Earth that take minutes or hours to arrive. Instead, astronauts could navigate in real time using the universe's own Lighthouse network. And the best part, this isn't just theory. Future missions could carry compact X-ray telescopes to lock onto pulsar signals, turning their steady pulses into a galactic roadmap. It's a game changer for deep space travel where getting lost isn't an option. So next time you look up at the night sky, remember, those silent, flashing stars might one day guide humanity to the stars. Now here's something that might surprise you: even these cosmic clocks aren't perfect. Every now and then, pulsars experience something called a glitch, a sudden, unexpected speed up in their rotation. Imagine a spinning ice skater pulling their arms in tighter, but in this case, the skater is a city-sized neutron star, and the change happens in a fraction of a second. These glitches might sound like tiny hiccups, but they're actually cosmic gold mines, offering us a rare peek into the bizarre physics happening inside these ultra-dense stars. So, what causes these glitches? One leading theory points to starquakes, yes, earthquakes, but on a neutron star. Picture the crust of a pulsar, a rigid layer just a few miles thick but as dense as an atomic nucleus. As the star spins down over time, this crust can crack under the strain, releasing pent-up energy and giving the star a sudden rotational kick. Another possibility involves superfluid vortices deep inside the pulsar's core. Neutron stars are so dense that some of their interior likely becomes a superfluid, a frictionless quantum state where particles move in perfect sync. If these swirling vortices suddenly unlock from the star's crust, they can transfer energy outward, speeding up the rotation like a hidden engine revving up. But why does this matter? Because glitches are like cosmic X-rays, revealing secrets about matter under conditions we could never recreate on Earth. By studying these anomalies, scientists can map the layers of a neutron star, the rigid crust, the superfluid core, and even stranger phases of matter that might exist at these extreme pressures. Some theories suggest there could be exotic states like quark matter, where protons and neutrons dissolve into their fundamental building blocks. Glitches also help us understand how pulsars slow down over time. Normally, their rotation gradually winds down as they lose energy to radiation and particle winds. But when a glitch occurs, it's like hitting a cosmic snooze button on that slowdown. Tracking these events helps astronomers refine models of pulsar evolution and even test predictions about how matter behaves at the edge of physics. So next time you hear about a pulsar glitch, remember, it's not a malfunction. It's the universe giving us a front row seat to some of its most extreme and mysterious phenomena. Now let's talk about what happens when these cosmic clocks finally wind down. Even pulsars, with their incredible precision, don't last forever. Over millions of years, they gradually slow down, their powerful beams of radiation growing fainter as they lose energy. It's like a lighthouse running out of power. The flashes become weaker, less frequent, until one day they stop altogether. But the end of a pulsar's life isn't always quiet. Some meet a dramatic fate as black widow pulsars. These are neutron stars that orbit so close to a companion star, they slowly devour it with their intense radiation and gravitational pull. Over time, the pulsar strips away its partner's material, leaving behind nothing but a faint, fading remnant. It's a cosmic dance of destruction where the pulsar ultimately outlives its companion and drifts into silence. Others face an even more violent end. In dense star clusters, two pulsars can spiral toward each other, locked in a gravitational embrace. When they finally collide, the result is catastrophic, a merger so powerful it sends ripples through spacetime itself. These collisions are some of the most energetic events in the universe, often producing gravitational waves and sometimes even forming a black hole. What's fascinating is that even in death, pulsars leave behind clues. The remnants of their collisions can create heavy elements like gold and platinum, scattering them across the cosmos. And the gravitational waves from these events help scientists test Einstein's theories in extreme conditions. So while a pulsar's light may fade, its legacy lives on, shaping the universe in ways we're still uncovering. Up next, we'll explore how these celestial timekeepers have inspired stories, art, and even our dreams of the future. Because pulsars aren't just scientific wonders, they're cultural icons too. But pulsars aren't just cosmic oddities, they've also sparked our imagination here on Earth. Across movies, books, and even music, these flashing stars have become powerful symbols in storytelling. Take the film Contact, where a pulsar's rhythmic signal becomes humanity's first clue that we're not alone in the universe. That steady, unnatural pulse, so precise it couldn't be natural, captures the awe and mystery of these celestial lighthouses. Then there's Doctor Who, where pulsars often serve as navigational markers or even plot devices, their unchanging rhythm acting as a cosmic heartbeat in the vastness of space. In sci-fi, they're more than just background scenery, they're beacons of hope guiding lost travelers or ominous warnings of danger ahead. The pulsar's duality, its relentless precision paired with its eerie, almost artificial glow, makes it the perfect metaphor for both wonder and unease. Even music has borrowed their cosmic cadence. The iconic cover of Joy Division's Unknown Pleasures album. That jagged pattern is actually the radio waves of a pulsar, CP1919, transformed into art. It's a reminder that these distant stars don't just tick like clocks, they sound like them too, their rhythms echoing through culture as much as through space. And let's not forget video games. Titles like Elite, Dangerous, and No Man's Sky use pulsars as waypoints or hazards, their intense radiation fields challenging players to navigate carefully. In every medium, pulsars bridge the gap between science and myth, turning hard physics into something poetic. What's fascinating is how consistently they're portrayed, whether as guides, threats, or messages from beyond. Maybe it's because, deep down, we recognize something familiar in their pulse, a rhythm that feels almost alive, a cosmic drumbeat reminding us that even in the void there's order. A pattern to cling to. Up next, we'll dive into the glowing clouds these stars leave behind pulsar wind nebulae and how they turn death into dazzling light. Because in space, even the end is just another kind of beginning. But pulsars don't just flash and fade, they leave behind something spectacular. Picture this, a supernova explosion tears apart a star, and in its place, a pulsar spins furiously, blasting energy into space. That energy doesn't just vanish, it lights up the surrounding debris, creating glowing clouds called pulsar wind nebulae. The most famous, the Crab Nebula, a swirling masterpiece of gas and light, all powered by the relentless spin of a pulsar at its heart. These nebulae aren't just pretty cosmic decorations, they're some of the most powerful particle accelerators in the universe. The pulsar's intense magnetic fields and radiation whip charged particles to nearly the speed of light, creating shockwaves that ripple through the nebula. It's like a cosmic factory, churning out high-energy cosmic rays, the same particles that zip through space and occasionally slam into Earth's atmosphere. What's wild is how these nebulae blur the line between destruction and creation. The same explosion that birthed the pulsar also scattered star guts across light years. But instead of fading into darkness, that debris gets lit up, energized, and transformed. It's a reminder that in space, death isn't an end, it's fuel for something new. And the Crab Nebula is just the beginning. Telescopes have spotted dozens of these glowing clouds, each with its own pulsar engine. Some, like Vela, stretch across space like ghostly jellyfish, their tendrils glowing with X-rays. Others, like G21.5-0.9, hide in plain sight, only revealing their secrets under the gaze of radio telescopes. But here's the real kicker. These nebulae might hold clues to one of astronomy's biggest mysteries, where cosmic rays come from. We've known for over a century that these high-energy particles bombard Earth, but their origins have been elusive. Pulsar wind nebulae, with their extreme environments, are prime suspects. They're nature's own particle colliders, far more powerful than anything we've built on Earth. So next time you see an image of the Crab Nebula, remember, you're not just looking at a dead star's remains. You're seeing a cosmic power plant, a natural accelerator, and maybe even a key to unlocking the secrets of the universe's most energetic particles. And speaking of energy, let's talk about what happens when pulsars push physics to the limit, because inside their cores, matter gets stranger than fiction. Now, let's step inside one of the universe's most extreme laboratories, the heart of a pulsar. Imagine squeezing the entire mass of a star into a ball no bigger than a city. The result, a place where matter doesn't behave like anything we know on Earth. Here, gravity is so intense that protons and electrons are crushed together, merging into neutrons. It's like taking all the empty space inside atoms and erasing it, leaving behind a dense sea of particles packed shoulder to shoulder. But it gets even stranger. Some scientists think that under these insane pressures, neutrons themselves might break down into something even more exotic: quark matter. Picture a soup where the usual rules of physics don't apply, and particles dissolve into their most basic building blocks. If this exists, it would be a state of matter never seen anywhere else in the cosmos. Pulsars are our only window into these bizarre conditions, offering clues about how matter behaves when pushed to the absolute limit. What's incredible is that we can study this from light years away. By measuring how pulsars spin, wobble, or even glitch, scientists can infer what's happening deep inside them. A sudden speed-up in rotation might hint at a starquake, a crack in the pulsar's rigid crust caused by the mind-bending forces at work. These tiny tremors reveal just how unstable and wild the environment inside a neutron star really is. And here's the kicker: pulsars might not just be made of neutrons or quarks. Some theories suggest even weirder possibilities, like strange stars, hypothetical objects made of strange quark matter. If these exist, they'd be denser and more stable than anything we've imagined. Pulsars are the testing ground for these ideas, pushing our understanding of physics to the edge. So while we can't recreate these conditions on Earth, pulsars do the heavy lifting for us. They're nature's ultimate physics experiment, showing us what happens when matter is pushed beyond anything we thought possible. And as we uncover more about their secrets, we're not just learning about stars, we're rewriting the textbooks on the very fabric of reality. Up next, let's explore how pulsars don't always fly solo. Some are locked in a cosmic dance with another star, creating systems that test Einstein's theories in ways he never imagined. Now let's shift our gaze to pulsars that don't journey through space alone. Some are part of breathtaking cosmic duos. Take the Hulse-Taylor binary system, discovered in 1974. Here, two neutron stars orbit each other at dizzying speeds, locked in a gravitational embrace so tight that their dance sends ripples through spacetime itself. What makes these pairs so special? Over decades, astronomers noticed something extraordinary. The stars were spiraling closer together, losing energy in a way that matched Einstein's predictions. The culprit: gravitational waves, the invisible ripples in the fabric of the universe. The Hulse-Taylor system became the first indirect proof these waves existed. decades before detectors like LIGO could catch them directly. But the tests don't stop there. Binary pulsars are like precision laboratories for extreme physics. As they orbit, their intense gravity bends time and space, slowing down or speeding up their pulses in ways that challenge our understanding. Some systems even show mind-bending effects, like one star's gravity stealing matter from its partner, creating violent bursts of X-rays. Perhaps the most thrilling moment comes when these pairs finally collide. The merger of two neutron stars isn't just a spectacular light show. It's a gold factory, literally. These crashes forge heavy elements like gold and platinum, scattering them across the cosmos. And thanks to pulsar timing, we can predict these collisions centuries in advance, watching as Einstein's equations play out in real time. So while solo pulsars are marvels, their binary counterparts take the mystery to another level. They're not just cosmic clocks, they're the ultimate probes for uncovering the universe's deepest secrets. Up next, let's tackle some common myths about pulsars and set the record straight on what these flashing giants really are and aren't. Now, let's clear up some cosmic confusion. Pulsars might seem like something out of a sci-fi movie, but they're not sending secret messages from aliens, no matter how tempting that idea might be. One of the biggest myths is that these flashing signals are deliberate attempts at communication. In reality, pulsars are entirely natural phenomena, born from the violent deaths of massive stars. Their rhythmic pulses are the result of physics, not extraterrestrial intelligence. Another common misunderstanding is about what we're actually seeing when we observe a pulsar. Many people picture them as flickering points of visible light, like distant lighthouses, but most pulsars don't shine in the spectrum our eyes can detect. Instead, they beam out intense radio waves or X-rays, which require specialized telescopes to observe. That's why astronomers rely on instruments like radio dishes or X-ray observatories to study them. These tools pick up what our eyes can't. Some even think pulsars are rare or short-lived, but the truth is, they're scattered throughout the galaxy, and many have been flashing steadily for millions of years. While they do slow down over time, their lifetimes are far longer than human history. So, the next time you hear someone suggest pulsars are alien signals or glowing stars in the night sky, you'll know the real story. These cosmic clocks are far stranger and far more fascinating than fiction. Up next, we'll look ahead to the future of pulsar discoveries and the incredible tools that will help us uncover even more about these mysterious objects. Now, let's turn our gaze to the horizon of discovery, because the future of pulsar research is brighter than ever. Imagine telescopes so powerful they can spot pulsars we've never seen before, hidden in the farthest corners of our galaxy. That's exactly what's coming with next-generation instruments like the Square Kilometre Array, or SCAR. This colossal network of radio dishes spread across 2 continents will be so sensitive it could detect thousands of new pulsars, potentially doubling or even tripling the number we know today. But it's not just about quantity. The SKA and other advanced telescopes might uncover pulsars that defy our current understanding of physics. Picture this: strange stars, hypothetical objects even denser than neutron stars, where matter crushes down into exotic particles like quarks. If these exist, pulsars could be the key to finding them. Every unusual flash or unexpected spin rate might hint at entirely new states of matter lurking in these cosmic extremes. And then there's the hunt for gravitational waves. Future pulsar discoveries could refine our ability to detect these ripples in spacetime, acting like ultra-precise buoys in a cosmic ocean. Tiny timing glitches in pulsar signals might reveal collisions between supermassive black holes or even phenomena we haven't dreamed of yet. The best part: we're on the verge of answers. Within the next decade, these telescopes will start feeding us data that could rewrite textbooks. Whether it's confirming wild theories or stumbling upon something utterly unforeseen, one thing's certain: pulsars still have plenty of secrets left to share. Next up, we'll explore how these cosmic clocks might hold clues to one of the universe's biggest mysteries, dark matter. Now, let's venture into one of the most intriguing puzzles in the cosmos. Could pulsars be the key to unlocking the secrets of dark matter? This invisible substance makes up roughly 85% of the universe's mass, yet it refuses to interact with light, leaving scientists scrambling for clues. But here's where pulsars come in. Their incredible precision might just hold the answer. Some theories suggest that dark matter particles, if they exist, could occasionally collide with pulsars, stealing tiny amounts of energy and causing subtle slowdowns in their spins. Imagine a cosmic game of pinball where invisible particles nudge these spinning stars just enough to leave a trace. By studying these minute changes in pulsar timing, astronomers might finally catch dark matter in the act. Then there's the even wilder idea pulsars could reveal hidden dimensions. If dark matter interacts with our universe through extra dimensions beyond the three we know, pulsars might show strange energy losses that can't be explained by known physics. It's like hearing an echo from a room you didn't know existed. Of course, these are still theories, but pulsars give us a real shot at testing them. Every unexplained glitch or timing anomaly could be a breadcrumb leading us closer to understanding the invisible fabric of the universe. And with next-generation telescopes sharpening our view, we might be on the brink of a discovery that changes everything. Up next, we'll meet some of the oldest pulsars in the galaxy, ancient timekeepers that have witnessed cosmic history unfold over millions of years. Now, let's turn our attention to the silent elders of the cosmos, pulsars that have been spinning for hundreds of millions of years. These ancient timekeepers, like Pulsar J0, 10, 8-1431, are cosmic relics older than most dinosaurs and still flashing with remarkable precision. At over 200 million years old, this particular pulsar is one of the oldest we've discovered. A faint but steady beacon from a time when Earth's continents were still unrecognizable. What makes these ancient pulsars so valuable isn't just their age, it's the stories they carry. As they drift through the Milky Way, their slow, predictable spins act like cosmic breadcrumbs, helping astronomers trace the galaxy's history. By studying their positions and movements, scientists can piece together how our galaxy has evolved, much like reading tree rings to understand Earth's past. These pulsars are like celestial archaeologists, quietly holding clues to the Milky Way's formation and the turbulent events that shaped it. But here's the twist: the older a pulsar gets, the weaker its signal becomes. Over millions of years, their beams grow fainter as their spin slows, making them harder to detect. Yet, even in their twilight, these ancient pulsars continue to teach us. Their very existence challenges our understanding of how long neutron stars can survive, and their subtle changes in rotation hint at the unseen forces at work in our galaxy. Next, we'll explore how pulsars might not just be cosmic clocks, but also potential message boards for civilizations beyond our own. Now, imagine turning these cosmic lighthouses into something even more extraordinary, a potential communication network for intelligent life beyond Earth. Scientists have long pondered whether pulsars could serve as natural message boards for advanced civilizations. Their precise, predictable flashes make them ideal cosmic beacons, almost like interstellar radio towers. If an alien civilization wanted to broadcast its presence across the galaxy, tweaking a pulsar's signal, say, by altering the timing or pattern of its pulses, could be a way to send a message visible to anyone watching. But the ideas don't stop there. Some researchers speculate that pulsars might even host alien megastructures, like Dyson spheres, hypothetical energy harvesting constructs built around stars. A pulsar's intense radiation could theoretically power such a civilization, and unusual dips or anomalies in its light might hint at artificial structures orbiting it. While no such evidence has been found yet, the search continues, blending the boundaries between astrophysics and the hunt for extraterrestrial intelligence. What's fascinating is how pulsars, already marvels of nature, could double as tools for cosmic dialogue. Whether as signal amplifiers or signs of distant engineering, they remind us that the universe might be far more interconnected and far stranger than we've ever imagined. Next, we'll reflect on humanity's own attempt to leave a pulsar-inspired mark on the cosmos. Now, let's take a step back and consider how humanity has already tried to leave its own mark among the stars, inspired by these cosmic clocks. In 1974, scientists at the Arecibo Observatory in Puerto Rico beamed a groundbreaking message into space, a deliberate attempt to communicate with any potential extraterrestrial civilizations. This historic transmission wasn't just a random shout into the void. It was carefully crafted, and at its heart lay a clever reference to pulsars. The Arecibo message included a map of our solar system, along with a diagram pinpointing Earth's location relative to a cluster of pulsars. Why pulsars? Because their incredibly stable flashes act like cosmic landmarks, unique, unmistakable beacons that could guide an advanced civilization straight to us. Think of it as leaving a trail of breadcrumbs across the galaxy, with pulsars as the signposts. But here's the intriguing question: was this a brilliant idea or a risky gamble? Some argue that broadcasting our coordinates could one day help extraterrestrials find Earth, sparking an interstellar dialogue. Others worry it might expose us to unknown dangers, like attracting a civilization with less than friendly intentions. After all, history has shown that when advanced societies encounter less advanced ones, the results aren't always peaceful. Yet, the Arecibo message also symbolizes something profound: our desire to reach out, to connect, and to declare, "We're here." Whether it ever reaches its intended audience or not, it stands as a testament to human curiosity and ambition. And who knows, maybe one day, a distant civilization will decode that pulsar map and follow it straight to our doorstep. Next, we'll explore how pulsars aren't just guiding potential aliens, they might also redefine time itself for future civilizations. Now, let's shift our gaze to something even more mind-bending: how pulsars could rewrite the very concept of time. These cosmic clocks don't just keep time, they challenge our understanding of it. For decades, atomic clocks have been the gold standard for precision, but pulsars, they're nature's own timekeepers, ticking with such regularity that scientists have seriously considered using them to redefine the second. Imagine a universe where our basic unit of time isn't based on atoms vibrating in a lab, but on the heartbeat of a distant star. What makes pulsars so extraordinary is their stability. While Earth rotation wobbles and atomic clocks need constant tweaking, a pulsar's spin is so consistent that over millions of years, its rhythm drifts by less than a second. This reliability has led to wild ideas, like creating a pulsar time standard for deep space travel. Future civilizations might not set their watches to Earth rotations, but to the synchronized flashes of these celestial metronomes. And here's where it gets even more fascinating. Pulsars could one day anchor a galactic calendar, a universal timekeeping system for civilizations spread across the stars. Picture a network of pulsars, each with its unique pulse pattern, acting like cosmic clock towers. By triangulating their signals, spaceships or colonies light years apart could stay in perfect sync, no matter where they are in the galaxy. But pulsars don't just offer precision, they also reveal the fluidity of time itself. Einstein's theory of relativity shows that time isn't absolute, it stretches and bends. Pulsars, especially those in binary systems, have helped scientists test these predictions with stunning accuracy. Their flashes arrive like clockwork, but when they pass through warped spacetime near massive objects, the timing shifts ever so slightly, proving that time is anything but rigid. So, the next time you glance at your watch, remember, somewhere out there, a pulsar is keeping time better than any human-made device ever could. And as we venture deeper into the cosmos, these flashing beacons might just become the heartbeat of our interstellar future. Up next, we'll wrap up our journey by reflecting on the mysteries pulsars still hold and why they continue to captivate us. As we bring our cosmic journey to a close, let's take a moment to marvel at what pulsars have taught us. These flashing beacons are more than just distant stars. They're the universe's most precise timekeepers, natural laboratories for extreme physics, and even potential guides for future interstellar travelers. From their eerie regularity to the way they bend our understanding of time itself, pulsars remind us that the cosmos is far stranger and more wonderful than we often imagine. Yet, for all we've uncovered, pulsars still guard their share of secrets. What happens inside their ultra-dense cores? Could they really help us detect dark matter or hidden dimensions? And might their signals one day reveal something even more extraordinary, like signs of other civilizations? Every flash carries not just rhythm but possibility, a reminder that the universe is still writing its story. So tonight, when you step outside, look up. Somewhere in that vast darkness, a pulsar is silently marking time with flashes older than humanity itself. These cosmic clocks aren't just scientific curiosities, they're invitations to keep exploring, to keep wondering. And who knows, the next great discovery might be hidden in their next pulse. If you've enjoyed this journey through the cosmos, don't forget to hit that like button and subscribe for more deep dives into the universe's greatest mysteries. Tap the bell icon so you never miss an update, and let us know in the comments what cosmic phenomenon should we explore next. Until then, keep looking up. The stars are always ticking.